See, most of the databases, what happens is we have various tables, we form various relations, and then let's just take an example. See this. Let us say we have an employee table. This contains all the information about the employee. Let us say this is the employee ID, this is the employee name, and maybe this is the department ID in which this particular employee works for. Employee number 1, whose name is A, works for department number 1, something like this. And now what should be this department ID? We know that it has to be a foreign key referring to the department, right? Now this department ID will refer to the department ID. These two fields need not have the same name. It is a good practice to avoid same names, even though they have the same meaning and even though they are same. It is better that you avoid the same names, because what happens is, okay, we shall see that later. Now department name, right? Now department number is 1, department name is, let us say, computer science. Okay, now if you want to see what is the department in which employee number 1 works, what is the name of the department, such kind of queries are very often possible, which means we have many relations or tables possible in our database, and then we might be having a query. Someone will be interested in knowing the information which might require going through many tables. For example, what is the department name in which employee number 1 is working. Then you have to find out the department number in which employee number 1 is working, and then you should go to that particular department number and then find out the name. So this type of queries are possible. So now then what happens is a kind of joining these two tables will be done, right? A kind of it. We shall discuss about it later. Anyway, when we have hundreds of tables, and if we have to continuously join the tables in order to answer many queries, then what is logical is, why should we make these many tables at all? The simplest database design will be putting everything together in one table. What is the advantage? No overhead of maintenance, right? You put them all together in just one table, have a universal table. Let's call it as universal table, which means I want to put everything that I have in my database in just one big table, right? Everything, either it is employee or department or like this. I'll have many columns. All the attributes will be kept in these columns and everything is kept in one big table. Let me call it universal table. Now what is the problem with this, or what is the advantage of this? See, information retrieval is easy now, because you need not go through many tables painfully. You can go to anything that you want and you can search for whatever they are asking. For example, if I have employee ID here and then employee number, and along with this, if I even put department ID and maybe department number, right? And if this department is also having some supervisor ID, right, then I'll have supervisor ID of the department also, everything here. Then if I need what is the department for which employee number 1 is working, then I can directly go to the department name and I can give this field, isn't it, without going through various tables. It is simple, and I need not break my head over how many entities are there, how many relationships are there, what are the attributes. Given the extract all the attributes and put them all in one table and it is done. You need not do anything else, right? But the problem with such a table is, there are various problems here. One simple problem is obviously redundancy, right? So redundancy is possible. Why redundancy? Because let us say a department is having 100 employees, right? Employee number 1, employee number 2, employee number 3, so on, 100 employees, right? Then I should continuously have the department ID, right? Let us say all of them are working for department number 1, whose name is computer science, and the superintendent name is that supervisor name is, let us say, supervisor ID is 10, right? Then I should have this information for every employee who is working for the department. In case if you would have had these two tables, then keeping this information in a separate table requires this information to be present at only one place, right? this ID will be repeated here, but then entire information will not be repeated. Therefore redundancy is there, so obviously there is wastage of space. Fine. Okay, anyway, let us say we have enough space and we want to go with this, but then there are lots of problems that will get arised whenever you try to insert something, delete something, or update something, right? They are called as anomalies. So one is redundancy, other problem with such a table is anomalies. So what are there are three types of anomalies. Okay, anomalies means problems, you can think of it that way. So what are the problems is, one is when you insert, there will be some problems, insert anomalies. So how will an insertion create a problem here is, assume that we want to insert a new employee with 101 who is also working for the same department, and you are trying to insert it. You have written the department ID as 1 and the department name is supposed to be computer science, but because of some mistake, some error, some typing error, let us say you have written it as ECE. Okay, now let's say by mistake, because of some error you have typed it as ECE. Then what happens is, the same department now in the database will have two names, and this insertion might go unchecked, which means database might accept it because it doesn't know where to check or how many tuples to check, and it doesn't know which one is right? So when you are having the same information at many places, there is a chance that it might get inconsistent. At one point, at one place it might show some information, and at some other place it might show some other information, right? Therefore insertion anomalies are possible, right? Next one is deletion anomalies. Deletion anomalies means, I'll just take an example here. Let us say I want to delete all the employees, all the 100 employees working for department number 1. Now no employee works for department number 1. Then what happens is, when you delete all the employees of department, then the department itself gets deleted, because there will be no entry which is containing the department number, right? So in case if you want to have that department even after deleting all the employees, then you might have to have only the department details, and in the place of employee details in that tuple you should have all the null values. And again you should keep track of whether I have deleted all the employees, or is it the last employee, or the first employee is added. If the first employee is added, then you have to modify this. It is going to be a very headache. It is all a overhead on the software. You have to make lots of checking, and the software code itself will become hectic, because writing the code itself is going to be a pain, because whenever you insert something, delete something, you might have to check the entire table, which sometimes may span to GBs or terabytes, right? So deletion is also going to create some problems. And then update anomalies means, whenever you try to, let's say modification, okay, or update analysis, update anomalies. So update anomalies means, whenever you try to update some entry, that might create a problem. For example, let us say you wanted to change the name of department number 1. From computer science department, you wanted to add something to the name of it. Let us say it is CS and IT now. The computer science department is now changed to computer science and information technology. Then what happens? You have to search in the entire database, and you have to see wherever computer science is written, and you have to change every name. It is going to be very, very painful, right? In case if this information is just present in one table like this, going there and changing it is very easy. It is like that hash define, isn't it? In C programming language, if you have a constant, it is always better that you will define the constant using hash define at one place, and you use that constant name wherever you want it. Later if you want to change it, just change that hash define, right? Similarly here, instead of having this throughout the database, just have it at one place. That will be better, isn't it? Okay, so these are all the problems which will occur if you try to reduce the overhead of designing the database by combining all the tables, right? So the solution is always simple. Divide the tables into as small tables as possible, right? Then how small should it be? Ideally, if you don't want any of these problems to occur, if you don't want any anomalies, or if you don't want any problems, the ideal size is 2 attributes, which means make a table in which every table has 2 attributes. If I have many such small tables, what happens is, in order to retrieve some information, I might have to go through hundreds of tables in some cases. Therefore, even though going for 2 attributes is always best, sometimes we can get the same results, I mean the best database designs, even without even with some bigger some bigger tables. You need not go till this small. See, going for attributes of a table which is containing only 2 attributes is the best thing. I'll tell you why later. That is called as BCNF. We shall see that later. That is the best thing you could do. But then, because of this design, the query time is going to be very, very high. So what other solution we have is, instead of going for so small tables, use some laws, use some formal methods in which you can get the same kind of good design even with a bigger table, but not with so big table, right? So now the solution for all these problems is to divide all the tables, not just this one. Even this table might also be having the same problems, right? There might be somewhere some duplication problem, or there might be somewhere anomalies. We don't know that. Take every table and see if it is good, test if it is good, test if your design is good, right? If it is not good, we are going to go for division or splitting the table, right? So that is called as normalization. Okay, so we are going to split the tables, divide the tables into small tables which will contain less number of attributes, in such a way that your design will not contain all these problems, right? In order to do that particular process, which is called as normalization, that procedure of dividing the tables is called as normalization. In order to do this normalization, we are going to use something called as functional dependencies, FD in short, functional dependencies, right? So we use functional dependencies and the concept of candidate keys. So you already know what is a candidate key, isn't it? So we use functional dependencies and candidate keys in order to evaluate formally. Formally means we have a well-defined procedure, right? Always formally whether a design is good or not. In case if it is not good, using some algorithms which are based on this functional dependencies, we are going to divide the tables, right? So once we know about the functional dependencies, once we learn about it, we can go for normalization. Okay, fine.